Now, before we start this video, I highly encourage you to make sure that you're pretty comfortable with polar functions and polar graphs. And so make sure you watch my videos on how polar functions and graphs behave before attempting any of these problems here. But with polar equations, they are going to operate pretty differently from rectangular functions, but what's really nice is that they actually perform pretty similarly to parametric equations. And so, although in BC, most of the time we're going to be using calculators to graph polar functions, it is a good idea for us to at least take a moment and make sure we understand how polar functions are graphed. And so we're going to do one by hand real quick. We're not going to spend a ton of time on this, but just make sure that we understand how these work. So if we look at something like 4 cosine theta, it's important for us to understand that r is giving us our distance from the pole, and our pole is another word for the origin here for a polar function, or on a polar graph, I should say. So r represents how far our value is from the pole, and it's a function of theta. So in this case, we have 4 cosine theta. So we're going to plug in these values that we have listed here for theta and see what we get for r. So in cosine of 0, when we're taking the cosine of 0 is 1. So 1 times 4 just gives us 4. And then when we have pi over 4, cosine of pi over 4 is root 2 over 2. And root 2 over 2 times 4 is 2 root 2. And we're going to just kind of rinse and repeat this. So go ahead and pause the video and just continue to fill out this table here for 4 cosine theta. And just to check, you should get the following here. These should be the values, unless I made a mistake somewhere, which is entirely possible, but let's just check. And I think those look good. So now we're going to go ahead and we're going to plot these values. So these are not x, y coordinates, but in the same way, for every angle theta, we have a specific r value. So when theta is equal to 0, our r value is equal to 4. And again, in my previous video, I went ahead and I went through how to plot these a little bit more in depth, but for all intents and purposes, we can kind of get a sense of what's going on here. For theta is equal to pi over 4, and pi over 4 is like right over here. When theta is equal to pi over 4, my r value is 2 root 2, which is approximately like 2.8. So it should be somewhere right around here. When theta is equal to pi over 2, which is up here, we have 0. When theta is 3 pi over 4, which is over here, we have negative 2 root 2. And again, remember when our r value is negative, that means we're going to reflect that value. So if it would normally be here, we're going to reflect it over the pole. So it ends up actually right around down here. So that's what it looks like for 3 pi over 4. When theta is equal to pi, I've got negative 4. So again, negative 4 would normally be over here, but because we're reflecting it over the pole, I'm going to end up back over here. So I'm just going to go ahead and connect these dots, and I'm not done here, but if I were to just go ahead and continue to plot those points, I would see that they would just kind of loop back around to this circle. And just hopefully see if I can make this a little bit larger here. There we go. All right, so that looks pretty good. So we see that this polar function actually just creates a circle. Now let's take a moment and let's think about what our x and y values are, or excuse me, x and y equations are. And the reason why this is important, why this can be helpful, is that we can rewrite our equations, our polar function, using the values of x and y to create parametric equations. And that's going to allow us to find the derivatives a little bit later, and we'll do that in a bit. So if you remember, x is equal to r cosine theta, and y is equal to r sine theta. So we're just going to write those equations. So x is equal to 4 cosine theta times cosine theta, or another way of just saying that is just cosine squared theta. And then y is going to be, what we have here is 4 cosine theta, or excuse me, 4 cosine theta times sine theta. And if you want to, you can use a double angle identity here to rewrite this as 2 sine 2 theta, but that's completely optional. Although doing that substitution might make your life a little bit easier a little later down the line when we're doing a little bit more with the derivatives. Now, what we're going to do is we're going to take those x and y equations that we have, and we're going to actually use them to plot our rectangular coordinates. And so we don't have to do this when we're graphing polar functions, but I just want to compare the two briefly. So for cosine squared theta means we're going to take the value of cosine of 0 in this first instance when theta is equal to 0. So cosine of 0 is still 1, 1 squared is still 1, times 4, and we end up with 4. And we're going to keep on doing this. The cosine of pi over 4 is still root 2 over 2, but since now we're squaring it, root 2 over 2 squared is going to give us 1/2, or 2 over 4. So 1/2 times 4, that's going to give us 2. And again, pause the video right now and go ahead and fill out the rest of the values for both x and y now. If you did that, you should get the following. -2, 0, and I think this one is actually 2 here. 0, -2, 4. Let's just make sure that's right. So I'm going to plot this in a separate color. So 4, 0, 2, 2, 0, 0, 2, -2, and we're going to loop back around. 4, 0, 2, 2, 0, 0, 2, -2, and we're back to 4. Right. And so if we would go ahead and plot all of our rectangular coordinates, we would get the same graph. We're doing it a different way. We're taking a different approach into getting these values, but we're still getting the same graph, whether or not we graph the polar function or our parametric equations here. Okay. So now let's shift over and let's get a little bit more comfort in graphing these functions using our graphing calculator. And this is going to be the most difficult part for me to try to show you how to do over this video lesson. But I'm going to just kind of talk you through it, and hopefully you can kind of work through it on your own. And if I have time, maybe I'll go ahead and publish some videos where I'm able to kind of sync up my calculator to this. But for this first problem, and we'll just try this first one here. For this first problem here, we're going to graph 3 minus 3 sine theta. A couple things to note. First off, make sure you hit the mode button on your calculator, and you switch your calculator to polar mode. That'll be the 5th row, go down to polar. Next, you also want to make sure that your function is in radians. You definitely can do this in degrees, but since it gave us our interval in terms of radians, we want to keep it in that for consistency's sake. Next thing, I'm going to actually also write out my x and y equations. This is also not really necessary for this problem, but just more practice. X would be 3 minus 3 sine theta times cosine theta, and y is equal to 3 minus 3 sine theta times sine theta. And we would say here, we're going to now plot this function. And when we are graphing this, a couple things to look out for. In your mode window, or excuse me, your window, you want to make sure that your t-min, or your theta min, I should say, your theta min, since it's in terms of theta, is equal to 0. And for theta max, go ahead and make that 2 pi. And for your theta step here, if you're on your Windows screen, there might be a default value there, but usually something around 0.1 just works fine. So if you graph this, then you should get something that looks like the following. You should get what looks like a cardioid, which is the name of this type of graph here. So this graph here is going to look something like this. And I'm just trying my best to not butcher this too much, but you should get something that looks something like that. That's not a great looking cardioid, but hopefully you get the idea here. So this is a cardioid. Think of cardioid because it kind of looks like your heart. Now, suppose you wanted to find dy dx, which is the slope of the tangent line at theta is equal to pi over 8, right? Theta is equal to pi over 8. So what we're saying here, when theta is equal to pi over 8, which, again, this is just a bit of an estimate here, which is right around here, when theta is equal to pi over 8, what we're trying to determine is what is the slope of this tangent line? And we're using dy dx to do that. So in your calculator, you want to go ahead and hit, and I'll just do this, write this to the side. We're going to hit the second button, then hit the trace. And then from there, after you've hit second trace, you'll then want to choose the dy dx option, and then just enter in theta is equal to pi over 8. And what you should get, if you've paused and tried that, is the following. And so that gives us an approximate value for the slope of our tangent line at that point. It's roughly negative, what it looks like, negative 0.2 or negative 1/5. And that seems to match up pretty well, even with this pretty terrible sketch that I have for this polar function. So hopefully you understand conceptually what's going on there now. So Now from there, now that we've had a chance to work through that, I encourage you to pause the video and try these other two and check your graphs with what I have uploaded to my classroom. All right, now that we have tried finding a couple of polar derivatives using our calculator, let's practice finding some polar derivatives by hand. So to find the rate of change of y with respect to x analytically using our polar coordinates, then we're going to need to use what we know about our parametric equations. So this is where us coming up with x and y, our equations for x and y, are going to be helpful. So just like we said with our parametric equations, we remember that to find dy dx, it's going to be the rate of change of y with respect to theta divided by the rate of change of x with respect to theta. Okay, so we're going to use that here. Now let's try that with this particular problem here. So we're going to say the following. Let's find the equation of the tangent line, meaning we're going to need to find the slope of our tangent line also, to the graph of r is equal to 2 minus 2 sine theta at the point 2, 0. And if you'd like, you can pause and graph this out in your graphing calculator so you know what it looks like, but we can do it without looking at the graph actually. So the first thing we're going to do is we're going to come up with our equation for x. So let me go ahead and kind of zoom in here on this. So our x is going to be, again, r cosine theta. So 2 minus 2 sine theta times cosine theta, which means that we can simplify this a little bit. 2 cosine theta minus 2 sine theta cosine theta, which then we can rewrite using a double angle identity, which we don't have to, right? We can though. Sine of 2 theta here. We can write that as sine of 2 theta there, okay? So, and if we wanted to leave that just as it is without using the double angle identity, we totally could have. And now that we have our x, let's go ahead and let's find dx d theta. So the rate of change of our x with respect to theta. So that's just the derivative of this. So that's going to give me negative 2 sine theta. And here now, actually having used the double angle identity makes our life a little bit easier here. So we can just say this is minus, take the derivative of the inside, which is 2, derivative of the outside, we're just applying the chain rule here, is the cosine of 2 theta. Okay, and again, you can use the double angle identity for cosine, but let's just leave that as it is until we know better what we're actually going to need to calculate. Next up, let's find our y equation. So we're going to say 2 minus 2 sine theta. This is our r value, or our r, times sine of theta. So this then gives me 2 sine theta times, or minus 2 sine squared theta. Now from here, let's find dy d theta, so the derivative of this. So from here, we're going to go ahead and we're going to then say this should be equal to 2 cosine theta minus, I'm applying the chain rule, 4 cosine theta sine theta. And so cosine theta sine theta. And if you want, you can rewrite this using some identities if you'd like. So we could say that this, for example, is equal to minus 2 sine 2 theta, however you please. But now let's go ahead and let's use this information to write the equation of our tangent line. So let me go ahead and make this a little bit smaller so I have some space to work with. So now that we have that, let's go back and now let's find dy dx. So what is dy dx? This is going to be, and you know what, let me just go ahead and make that substitution now while I'm at it. There. So dy dx is going to be all of this, dy d theta, divided by dx d theta. Put that down here. Now, this is our dy dx. And what are we using our dy dx for? We're using it so that we can find the slope of our tangent line of this graph at the point 2, 0. So what we need to do is we need to evaluate our dy dx at the point 2, 0. Now, this presents initially a bit of an obstacle here because we're looking at the point 2, 0, but our derivative is in terms of theta. Fortunately for us, this is an easy fix. So let's just ask ourselves, what is theta when we're looking at the point 2, 0? And You could normally plug in one of these values in for either your x or y equation and solve for theta, but fortunately for us, we don't have to, because if the point is at 2, 0, just ask yourself, when our point is at 2, 0, what is our theta? If it lies right on our x-axis, that means theta must be equal to 0. That's the only way we can get the point 2, 0 here, right? So if that's the case, then what we're going to do is we're going to evaluate this derivative at theta is equal to 0. So let's do that. So when theta is equal to 0, cosine of 0 is 1, so 2 times 1 is 2. Anytime we take the sine of 0, we're going to just get 0, so we don't have to really worry about that. And in the denominator, we've got another sine of 0, so that's going to give us 0. And now we got 2 cosine 2 theta. Well, again, cosine of 0 is just going to be 1, so negative 2 times 1 is negative 2, and that just gives us negative 1. This is the slope of our tangent line. So now that we have the slope of our tangent line, we're ready to write our tangent line equation. We can say y minus y1, we're going to use our coordinate 0, is equal to negative 1 times x minus our x coordinate 2. And there's the equation of our tangent line. Now in the next lesson, we're going to do a little bit more practice with this, but we are going to look at some unique instances of what's going on with our tangent line.